Right, we're doing some demonstrations with static electricity, and one of the simplest demonstrations you've probably seen or tried yourself is if you rub a balloon on your hair, it'll stick to the wall. Let's try it. Rub it. Sticks to the wall. How does that work? Well, what we're actually doing there is the balloon is made of atoms. Atoms are made of protons, neutrons and electrons. Protons and neutrons are locked in the nucleus. Electrons are orbiting around the outside of the nucleus. So when you rub two surfaces against each other, electrons will move from one of the surfaces onto the other one. For example, electrons will jump off my hair onto the balloon. Now that balloon is now got a load of excess electrons on it. So when I bring it close to the wall, those electrons will repel other electrons in the wall, and then the electrons in the balloon will be attracted to the protons that are in the nucleus of the atoms in the wood. So it's repelled the electrons and it's attracted to the positive charge in the nucleus of the atoms. Static electricity. Here's another nice wee example. We've got a balloon here. Now the balloon's got equal numbers of positive and negative charges on it, so it's electrically neutral. Overall it's neutral. It's got balanced charge on it. But if I rub that balloon on my jumper, electrons from my jumper go onto the balloon, and if I let the balloon go, it'll be attracted back to the jumper again. But if I bring it close to a wall, watch what happens to the wall. The balloon is pushing electrons away from the wall, and then the negatively charged balloon is attracted to the wall. That's why a balloon sticks to a wall when you rub it on your hair or rub it on your jumper, and the negative charge on the balloon sticks to the positive charges in the wall. Opposites attract. So remember, everything is made of atoms. This polythene rod is made of atoms, this duster is made of atoms, and atoms themselves are made of protons, neutrons and electrons. The protons and neutrons are locked in the nucleus and electrons are orbiting round the nucleus. And by rubbing one object with another object, you can remove electrons from one substance and place those electrons on the other substance. So if I rub this polythene rod with a duster, electrons jump from the duster onto the rod, and that rod has become negatively charged because it's got extra electrons rubbed onto it, and those electrons are negatively charged. Now we can see that by using this little meter here. This is a meter that measures electric charge, and electric charge is measured in a unit called coulombs. So this is a coulomb meter, and just now it's reading 0. But if I rub my rod and then scrape it onto that meter, then it's giving us an indication of how much negative charge, although it's billions of electrons, it's billions of electrons in a coulomb of charge, then at least we're getting an indication to show us there that there's a build-up of negative charge on that polythene rod. Now, just like magnets, if you have two magnets that are the same, then they will repel each other. So if I get two polythene rods and I rub one of them and then I place it on this glass slide, and then I get another polythene rod and I rub it as well, then both these polythene rods are negatively charged, and if they're both negatively charged, they should repel each other. So imagine to push one polythene rod with the other polythene rod just because they're both negatively charged, and the negative charge on one of them is repelling the negative charge on the other one. There you go then, a static electricity. It's called static electricity because that charge, those electrons that we've rubbed onto the rods, once they're on the rod, they don't go anywhere. They're stuck. They've got nowhere to go. And just like when I rubbed my polythene rod onto that coulometer, those electrons have got nowhere to go, so that meter will stay charged with all that negative charge, unless I connect a wire from here to here and allow those electrons, allow that charge a path to escape. So if I touch that there, then all those electrons will flow off the metal plate and we've emptied it out of its static electric charge. Now this is probably everybody's favourite demo at school. It's called the Van de Graaff generator. And the Van de Graaff generator works on the principle of static electricity. It's got an elastic band in it, a big rubber band. You can see it inside that clear plastic tube. And what that elastic band does, when you turn on the Van de Graaff generator, the band rubs electrons off the dome. So the dome loses electrons and becomes positively charged. So just now what's happening is that rubber band is removing electrons from the dome. The dome becomes positively charged and it wants to get electrons from somewhere else. So if I bring my hand close to that dome, then a spark will jump from, now the spark actually jumps from my hand to the dome. Let's see if we can zoom in there and see that. Electrons, because the dome's positively charged, the dome wants electrons, so it takes them from my hand. Oh, you dirty dog. So let's see if we can show you a spark or two coming from the surface of the Van de Graaff generator. Oh, you dirty dog. And usually if folk were in school, we would get somebody standing and putting their hand on top of the Van de Graaff generator and their hair would stand up. And the reason that their hair would stand up is because they get electrically charged as well. They would get positively charged. They become part of the dome, and because their hair is all positively charged, then all their hairs repel each other. Watch this. So all those hairs are sticking up because they're all repelling each other. They're all positively charged. And they want to get as far away from each other as they can. And if I bring my hand up close to that dome, and watch what happens. So by bringing my hand in, electrons from me have moved on to the dome, and the hairs are no longer repelling each other. So all my negative charge has cancelled out that positive charge. But if I take my hand away again, it builds up that positive charge again. There's two types of electric charge, positive and negative. Like charges will repel each other, so two positive charges will repel, or two negative charges will repel as well. And opposites attract. Similar to magnets. That's pretty cool. And static electricity is called static electricity because it's stationary, it's got nowhere to go. And it's only when you give those electric charges a path to move that they can flow and you get current electricity. Current electricity is a flow of electric charge, and electric charge can carry energy. I've put some wee metal cup cake holders, like mince pie cases, on top of the Van de Graaff there. Now they're just sitting on top of each other and they're just sitting on top of the dome. If I switch the Van de Graaff generator on, remember the dome's going to become positively charged. And if the dome becomes positively charged and that positive charge has got nowhere to go, then the cases will become positively charged and they will repel each other. Watch this. Ready? So the cases became positively charged, the positive charge repels other positive charge, and the cases force each other off of the top of the dome. Electric charge produces a force, and that force can make charges move. Here's another nice wee demo. I've got some wee metal balls inside that plastic tube there. Just little silver paper balls. And If we switch on the Van de Graaff dome becomes positively charged. The little silver balls will become charged and they will be repelled away. Let's turn it on and see what happens. Look at that. And those silver balls get repelled away from the dome and they hit the metal plate at the top, and the metal plate at the top eventually becomes positively charged. So, if the dome is positively charged and the metal top is positively charged, they then get into a balanced state where they've got nowhere to go. Unless I bring my finger up. I'm going to bring my finger up to the top plate. Watch this. There we go. It's all balanced again. Bring my finger back. I'll come back in 6 years and we'll tell you more about that. That's magic. Okay folks, here's the theory then. We need to go back and have another wee look at the structure of the atom. It's very important for when we're talking about electricity. So remember, atoms are made of three smaller particles, the protons, the neutrons and the electrons. The protons are locked in the nucleus and they have a positive electric charge. Neutrons are also locked in the nucleus and they're electrically neutral. And those electrons are only loosely held in orbit around the nucleus and they have a negative electric charge. And that's a typical diagram that you'll see whenever you're shown a simple diagram of an atom with orbiting negative electrons. So there's two types of charge, positive and negative. A proton has a positive charge, an electron has a negative charge. And those diagrams have got arrows on lines that are surrounding those charges, and those lines and those arrows will show you the direction that a positive charge would move if you brought it close to either of those central charges there. So if you brought a positive charge close to the positive charge in the centre of the diagram on the left, it would be repelled away from it no matter where you placed it. And if you brought a positive charge close to the negative charge on the right, it would be attracted to it no matter where you placed it. So the lines and the arrows show the direction that a positive charge would experience a force. And there's no neutrons on this slide because remember, neutrons are neutral and they don't appear to have any electrical charge. Like charges will repel each other and opposites will attract. So on the left there, we've got a positive and a negative charge. They're attracting each other. Two positive charges will repel. Two negative charges will repel. Now, most substances are electrically neutral, not because they've got no charge, it's because their atoms contain equal numbers of positive protons and negative electrons. But if you rub a material, it can cause electrons to move from one substance to another. So in this diagram, we are rubbing a rubber rod with a piece of fur, and the fur loses electrons and becomes positively charged, and the rod gains electrons and the rod becomes negatively charged. So this build-up of charge on a material is called static electricity. It's called static electricity because it doesn't go anywhere. Let's show you this wee simulation from our friends at FET. Right, here's our friend John Travolta then. John is standing on a carpet and he's going to rub his foot on the carpet. And what do you notice when he rubs his foot on the carpet? Then the electrons move from the carpet onto him and they've got nowhere to go. Unless, of course, he touches the door handle. And when he touches the door handle, those electrons have then got a path to move and they escape from him. Nice. So, he's filling up with static electricity. It's got nowhere to go until we provide the path for the negative charge to move. Lovely. So the Van de Graaff generator then. There's a nice diagram of the Van de Graaff generator showing you the rubber band, the conveyor belt that rubs electrons off the metal dome, and the dome becomes positively charged. And if you bring your hand close to the dome, a spark can jump across the gap between your hand and the dome. Oh, you dirty dog. That spark is the result of negative charge electrons jumping to the dome. So an electric field then is a region where a charge experiences a force. A lightning storm's an example of where charge moves in an electric field. Static charge builds up on the clouds, and this is due to the water molecules rubbing against each other so that one cloud becomes positively charged and another cloud becomes negatively charged. When there's a big enough electric field, electrons will move through the field as a lightning bolt. Here's another example of some electric field patterns. Again, the lines and the arrows show you the direction that a positive charge would move if you placed it anywhere in the field. And we can produce electric fields in the classroom using a very high voltage supply. So a uniform field, uniform just means it's the same at all points, and a uniform field exists between the positively charged terminal and the negatively charged terminal of the apparatus. So negative charges in an electric field will always move away from a negative terminal and towards a positive terminal, and this is the principle behind electricity. Metal wires and other conductors contain electrons that are only loosely held in their atoms. So if you use an electric field can cause those electrons to move, and moving electrons can carry energy. So a battery produces an electric field that pushes electrons out of the negative side of the battery, and it pushes those electrons around to the positive terminal of the battery, and those moving electrons transport energy. So in an electrical circuit, the negative charges are pushed around the circuit and they carry energy from where they are stored in the battery to where they are required. And the electric field in a battery is produced by a chemical reaction, and that's chemistry.